Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be setting up flow through a proportional valve here. Now I've already made the geometry and this geometry has also been shared with you in STL file. You can use it and you can set up the case along with me. This case study is based upon the paper CFD simulation of a safety relief valve for improvement of a 1D valve model. And I basically use this paper because it does a great job of explaining why computational fluid dynamics analysis is important when it comes to valve applications. Now in this particular case, the author has basically taken up valves that are commonly used for nuclear engineering applications where the valve life has to be determined correctly, and no matter what happens, leakage is completely not allowed. So as some of you might know, proportional valves are used to limit pressures. As the valve becomes overused, then it can start to leak and it can cause unpredictable performance. Now in case of nuclear engineering applications, this can actually lead to fatal incidents. So it's extremely important to have a very good idea about the valve opening dynamics and the valve characteristics. So in this particular case, we will be setting up a proportional valve. So the proportional valve is a valve where the valve lift depends upon the inlet pressure that is being subjected on the valve spindle. So in this particular case, you can see a cutout of the valve, and this right here is called as the valve spindle. Now this is the inlet, so the fluid is going to come through the inlet and it's going to push open the spindle. The higher the fluid pressure, the higher the valve lift, right? So this is what you call as proportional valve, and the name proportional basically says that the lift is proportional to the inlet pressure. So this is another diagram that helps you understand how this works. So for example, fluid comes through the inlet, it's basically going to push open the valve, and you can see that there are a couple of forces that acts against the fluid pressure. One is the gravitational force and the other force is the hydraulic force, and then the spring force. Now as far as our simulations are concerned, we will be doing a two-part study. In the first study, we will basically be looking at the flow characteristics at different valve lifts. So for doing such a study, we don't have to use any type of fluid structure interaction model. In the second part of the study, we will be using an FSI based model which will actually help us provide a spring force that will basically resist the inlet pressure. Now in addition to this, there is a third study that is possible where we can actually modify the spring force based upon the valve lift. However, that requires a user defined function which is not covered in this course. And if you scroll down the paper a little bit more, you will be able to see the spring stiffness and also the preloading. So preloading is basically the initial tension that's actually acting on the valve. So the fluid pressure must impart a force that's greater than 7,126 newtons in order for it to lift the valve. Alright, so with that, let's just get started. So here you can basically see that I already have my geometry. Now clearly you can see that the dimensions here are not correct. That's because this is all in millimeters and Converge assumes that the geometry should be in meters. So let's go to transform, scale, and apply a scaling factor of 0.001, and we would want to apply that to the entire body. Once you do that, the geometry disappears. Click on the standard view icons to bring the geometry back. Now in first glance you will see that this doesn't look like the original geometry. So what you can actually do is maybe put the geometry in top view and then use the box selection tool, select roughly one half of the geometry. Oops, I'm in vertex selection mode. I'm going to use the keyboard shortcut 3 to go to triangle selection mode, draw the box one more time, and use the shortcut key Ctrl H, or alternatively you can right click and select hide selection. So now if you look at this, you will basically see that this represents the cut section that we had looked at earlier, and you have to basically zoom in close to see that the solid components of the pipes have also been included, which is not required. So I'm going to hit redisplay, and my objective here is to make sure that I get only the fluid volume. Basically, if you assume that water is flowing through the entire valve, you need the surfaces that are in contact with water. So for example, if you take this external surface, which I can maybe select by selecting a few triangles. So this external surface is not going to be in contact with the fluid, right? So that would be something that you would not want. So first I'm going to get rid of the unwanted boundaries. So there are multiple ways to do this. For me, the easiest way always is to first start by creating a few boundaries, and initially I go about creating 7 to 8 boundaries, and you can always delete unused boundaries. So I'm going to start with boundary number 2, and I'm going to use the angle option to see if I can select the internal faces one by one. So there you can see that I've selected one face, I've selected one more. Now I'm just going to try and see how much I can select manually, right? So that's another internal face. I think that's pretty good. So let me click on apply, and that's basically my internal face. So I can go to view options and I can just hide that to basically get rid of it. Similarly, in parallel, what you can do is you can click on the external faces that you don't want. So for example, I don't want this and I also don't want this thickness. Make sure that you're really careful with your selection and hit delete, right? And if I'm going to redisplay everything, I should be able to get only the fluid volume. Similarly, this is not required. Make sure that you rotate the model and see that you've selected only the components that you want. Hit delete and do the same thing for this guy and maybe for this one as well. Let's hit delete. Okay, so far so good. So here things might start to get confusing a little bit. So when it does, always look at the geometry from outside. So for example, this right here is going to be your inlet, correct? So you would want this particular face, but you would not want this thickness and also this part. So let's delete that. Okay, and coming to the top, what I'm going to do is I'm going to click on this guy and delete that, because that's something that that is something that I won't need. And as you're deleting, right, you will see that the inner volume would be made up of perfectly connected components. So that also gives you a clue, which means this can go directly. And here you can see that perfect connections are made, and something weird is happening here. So we'll get to this component, but this part that is attached with the open edge, that basically belongs to the solid, so you can delete that, right? So now what you can do is you can look at the geometry from top view, draw the box one more time, use Ctrl H and see if this actually makes sense, right? And the cut view can also help you figure out which components need to be deleted out, right? So here you can see that there is this open edge, right? And this basically belongs to the solid. So I can go back to repair, delete, use the angle method, and I'm going to see if I can select this guy and this guy and this guy and finally this guy, right? So I think with that I got rid of all the components that I would not need. So you can see that there are a few missing components here, so just handpick them and go ahead and delete them manually. And we have a few more right in the bottom. Okay, so now let me redisplay the geometry. So what I should see is I should see two sets of open edges, one for the inlet and one for the outlet. So what I can do is I can use the patch tool, and I'm going to go with list of open edges, and I'm going to select this guy. And when I'm patching it, I'm going to assign it to a new boundary. However, now that I think about it, that option is not going to work. So let me just check that option out. Click on apply. So it's going to create a new boundary. I'll quickly go to boundary flagging. I'll use the new boundary and I'll add it to boundary number 3. And let's do the same thing for this guy as well. Now you can go to repair patch, or you can use the shortcut. Press the button 2 and then you see that you're still in open edge. Click on this guy. Use the shortcut key P, and that's going to patch. But however, the newly created boundary is automatically flagged with boundary number 1, which sometimes can be okay, but in this case it's not. So I'm going to go back to triangle selection mode one more time. I'm going to use the angle method, select this guy, and I'm going to add that to a new boundary. Okay, so now let's run the diagnosis. You can see that the only issue that we have is the normal orientation. Let's display the normals, and you can see that the normals are pointing out, which is wrong. So let's go to transform normal, select this guy, click on apply. So now the normals should all be pointing inside, and if you click on find, all the problems have been fixed, right? So that completes the geometry creation part. In the next video we are going to be doing the case setup for the steady state simulation. All right, so I'll see you guys in the next video. Bye.